Sodium oxide is a substance toxic for human beings which can even cause death if ingested or absorbed through the skin. It is dangerous if it is inhaled, and it may cause irritation on the skin if it gets in contact with it. It can affect the central nervous system, kidneys, and the cardiovascular system. On a scale of 1 to 4, it has a health risk of 3, an inflammability risk of 2, a reactivity risk of 4, a contact risk of 3. For this reason, it is important to take safety measures when handling this substance. Goggles, lab coat, and gloves are mandatory. In case of inhaling it, the person must be taken to fresh air or given artificial breathing if the person is no longer breathing. If it is ingested, vomiting must be induced. Contact with the skin and eyes must be thoroughly washed with water for at least 15 minutes. Medical attention should be provided immediately. The substance must be stored in a fresh area and well ventilated away from heat. It is an ionic compound. Sodium is a metal. In case of inhalation, the person must be taken to fresh air or given artificial respiration. If it is ingested, vomiting should not be induced and abundant water should be drank. Contact with the skin and eyes must be thoroughly washed with water for at least 15 minutes. Ingestion is particularly dangerous as it can produce burning and even a hydrogen explosion. The substance must be stored in a fresh area well ventilated away from heat. On a scale of 1 to 4, it has a health risk of 2, an inflammability risk of 2, a reactivity risk of 0. It must be kept away from flames and water. To handle it, safety equipment should be used. Nitrogen is gaseous at standard time and pressure. Ingestion and contact do not have negative effects, but high concentrations of this gas may cause suffocation. It has a health risk of 1, an inflammability risk of 0, and a reactivity risk of 0. However, using goggles is advised. In case of inhalation, the person must be taken to fresh air or be provided artificial respiration. Medical assistance should be sought. Potassium nitrate is a white powder at standard time and pressure. It is an oxidizing agent that can cause irritation and burning if it gets in contact with the skin. Inhalation will irritate the throat, and ingestion will cause abdominal pain, vertigo, difficulty to breathe, and it can make skin turn blue. On the long run, it may cause kidney failure. It has a health risk of 2, an inflammability risk of 0, a reactivity risk of 0, and wearing goggles, gloves, and a dust respirator is advised when handling this substance. In case of contact, medical assistance should be sought immediately. In case of inhalation, the person must be taken to fresh air or be provided artificial respiration. In case of contact with the skin and eyes, should be washed with abundant water for at least 15 minutes. If it is ingested, abundant water should be drank and vomit should not be induced. Sodium oxide is a white powder at the standard time and pressure. It is a corrosive agent with a very high pH. Inhalation may cause coughing, burning, and difficulty to breathe. It can also be the cause of pulmonary edema. Contact with the skin may cause pain and even be the cause of severe burning. Medical assistance is recommended in any case. It can react violently with water. It is not combustible. In case of inhalation, the person should be taken to fresh air or be provided artificial respiration. Contact with the skin and eyes should be washed thoroughly with water. If it is ingested, the water should be washed and vomit should not be induced. Potassium oxide is a crystalline dust at standard time and pressure. It is not combustible, but it is corrosive, and in a solution, it reacts violently with acids. Contact with the skin may cause irritation, pain, and severe burning. Inhalation may cause irritation in the throat, coughing, burning, difficulty to breathe, and even pulmonary edema. Ingesting it will produce pain, shock, and burning. It has a health risk of 3, an inflammability risk of 0, a reactivity risk of 2. In case of inhalation, the person should be taken to fresh air or be provided artificial respiration. In case of contact with the skin and eyes, the area affected should be washed thoroughly with water. If it is ingested, the mouth should be washed and abundant quantities of water should be drank. Vomiting should not be induced. Medical assistance should always be sought. Silicon dioxide is a white powder at standard time and pressure. It may cause irritation on the skin through mechanical effects. Ingesting the substance has no known effects. Inhaling the dust may cause difficulty to breathe. It has a health risk of 1, an inflammability risk of 0, and a reactivity risk of 0. However, goggles, gloves, and a dust respirator are suggested when handling this substance. In case of inhalation, the person should be taken to fresh air or be provided artificial respiration. If it is ingested, potassium silicate is a substance miscible in water. A solution of this compound is a translucent pink. It is not carcinogen, but it is not known if it is mutagenic or teratogenic. In case of ingestion, vomiting should not be induced, and medical assistance should be sought immediately, and abundant water must be drank. It may cause irritation in teeth and in the esophagus. It has a health risk of 1, an inflammability risk of 0, a reactivity risk of 0, and wearing gloves is advised when handling this substance. Sodium silicate can be dangerous to ingest or inhale. It can also irritate the skin and may be the cause of severe burning. Any contact with the skin and eyes should be thoroughly washed with water for at least 15 minutes. If it is inhaled, the person should be taken to fresh air and medical assistance should be sought immediately. If it is ingested, abundant water must be drank and vomiting should not be induced. To handle it, you must use a dust respirator and protective garment. It has a health risk of 2, an inflammability risk of 0, and a reactivity risk of 0.
So here we have the elements and compounds that we're going to use in our reactions. So here we can observe the enthalpies of each one of them. We can see that the ones that are positive are an endothermic reaction, and the ones that are with the negative sign are the ones that are exothermic. We can see that these 4 are the exothermic, while this one is the endothermic. And over here we have our entropies. Our entropies just define the amount of order. Least amount of entropy means that there's more order in the reaction. So we can see that the one with the most disorder is the nitrogen, when the one with the least disorder, so the more order is this one. So we already talked about the elements, and now we're going to talk about the reactions that happen in an airbag. In an airbag there are 3 reactions. This one being the main one, and these 2 being the secondary ones. The main one is the one that inflates the airbag full of nitrogen air. And we can see over here that the entropy and enthalpy of each of the reactions. We can see that the entropy of the first reaction, as the main one, is with a positive sign. That means that there's a lot of disorder in that reaction. And we can see that in this one it's also positive, so there's a lot of disorder. So that may help us make the assumption that in the third one is going to be also a disorder. And going over here, we can see that the enthalpy of the first reaction of the main one is negative sign. That means that it's an exothermic reaction. And we can see the same thing happening in the second one. That means that we can also assume that the third one is going to be also an exothermic reaction.
Right now we're going to calculate the Gibbs free energy, which is calculated through the following equation. Delta G equals delta H, which is the enthalpy, and minus T, which is the temperature, multiplied by delta S, which is the entropy. Here we're going to do it for the first reaction with the values we already got, and what we get is a negative Gibbs free energy, which means the reaction is spontaneous. We will do it again for the second reaction, and we also get a negative result, which means that that reaction is also spontaneous. We couldn't find some of the values to make the operations to get the enthalpy and the entropy for the last reaction. However, we can assume that the enthalpy will be negative and then the entropy will be positive, and thus the Gibbs free energy will be less than 0 and the reaction will be spontaneous.
Now we want to know the quantity of the reactant needed, that is sodium azide, to carry on the reactions that make the airbag inflate. To do this, we assume three things. The first, that the front face of the airbag begins at rest, that is an initial velocity of 0 meters per second, that it's traveling at 89.4 meters per second, and that by the end of the inflation it has traveled 30 centimeters. This is the approximate thickness of the airbag. With this equation, we solve for A, the acceleration, and we get that acceleration equals 1.33 times 10 to the 4th meters per second squared. We measured in real life that the approximate mass of the airbag is 2.5. So the force exerted on an object is equal to the mass of the object times its acceleration. So we can find the force with which the gas molecules push this airbag forward to inflate it so rapidly. We substitute in our values, and we get that the force equals 3.33 times 10 to the 4th newtons. Now, we calculated some data in real life with an airbag. We got that the area of the base, that is this circle right here, is 0.24 meters squared. And the height, or width, is 8.6 centimeters or 0.086 meters. We use this information to calculate the volume. We get that the volume equals 20.74 liters. Pressure is defined as the force exerted by a gas per unit area on the walls of the container. So the pressure in pascals that we get in the airbag immediately after the inflation can easily be determined using the force calculated above and the area of the front face of the airbag. We must note that the pressure we're going to calculate is the gauge pressure. So the gauge pressure equals force over area. We substitute our values and we get an answer in pascals. We divide that by this quantity right here, and it equals 1.3693 atmospheres. Then the amount of gas needed to fill the airbag at this pressure is then computed by the ideal gas law. But we have to use the absolute pressure, and to calculate the absolute pressure, we add the gauge pressure and the atmospheric pressure. That is 2.3693 atmospheres. And finally, we use the ideal gas law, PV equals nRT. We have our data, the pressure, the volume, the constant R, and we assume that it happens at 25 Celsius degrees, that is 298 Kelvin. We clear for N, substituting our values, and the answer is 2 moles of sodium azide. But what we need is the quantity in grams. So we do the conversion, 2 moles of sodium azide, and for 1 mole there's 50.98 grams. So we do the simple calculation and we get that we need 101.96 grams of sodium azide to carry on the reactions. We can see also that the 2 moles correspond to the coefficient of sodium azide in the first reaction right there. Inside the airbag, there's a gas generator containing a mixture of sodium azide, potassium nitrate, and silicon dioxide. So first we have the first reaction and its corresponding physical constants for each product and reactant. And what happens here is that after the accelerator sensor detects the shock, an ignition caused by a spark plug causes the sodium azide to turn into sodium and nitrogen gas. The nitrogen gas is responsible for filling the bag to soften the impact of the driver. And the whole purpose of the potassium nitrate and silicon dioxide is to convert the sodium metal into a harmless material, and it's done with the second reaction. So because sodium metal is highly reactive and potentially explosive, potassium nitrate and silicon dioxide must be added to make it a non-hazardous material. First, the sodium reacts with the potassium nitrate to produce potassium oxide and nitrate oxide, and more nitrogen gas that is used to fill the bag. We can see right that here. And finally, then it reacts with the silicon dioxide to produce silicate in the form of glass in a very fine powder presentation.
We need to be very careful of how we handle airbags, because sodium azide is odorless. It is very dangerous for the drivers because it is very difficult to detect it. After reacting, one of the products besides the nitrogen gas is a sodium metal dust that can spread easily in the car after explosion. If the space is very confined, the sodium fine dust can be breathed by the passengers. This will eventually get into the lungs alveoli, causing asthma or intoxication, and even weeks after the explosion of the airbag, it can trigger pneumonias or cardiopulmonary failures. Also, it may be very dangerous because if the driver loses consciousness, it may take time for the help to arrive to the place of the crash, leaving the driver more time exposed to the fine dust.
So my reflection in the way that the chemical reactions carried on inside the airbags help save lives is mainly due to two things. One is that the expanding gas inside the nitrogen gas inside the airbags helps the force that the driver is carrying be exerted on a larger area instead. That's meaning in the airbag instead of on the wheel or something, and that it's also like fluffy in a way that the strike, the hit, is not as hard on the airbag as it would be on the wheel or with the glass or or another part of the car. And the precautions that we must have with the reactants and products that are used in these reactions are mainly due to their toxicity to humans. They can be hazardous, and so they must be turned into another compound almost right away, so there are no leftovers of toxic compounds for humans. And I think that the best way to dispose the leftovers of these chemical reactions so they don't pollute the environment is to also use chemicals that do not pollute the environment that neither. Use these chemicals to turn them into something useful to life, to the earth. And my message on the importance on understanding the properties and transformations of matter in this context of processes that occur in our daily lives, like in the airbags, is we should understand how the gases work, because they're all around us. In the atmosphere, everything is air. Well, most of the mass in the atmosphere is air, so they're everywhere. They're used in medicine and physics, chemistry. They're pretty much basic to all sciences, so we should know how they work, how they react to things, to physical properties, chemical properties, so we know how to react in case of danger or use them in our favor in case we need to solve a problem.
In order to avoid having an airbag exploding,
and releasing sodium acid during the recycling process, it is necessary to remove the airbag canister in order for replacing it in a safer place. If this step is not done as the car is crushed or flattened, the toxic component can be released into the air, affecting the workers. According to government's law, the airbags must be placed in metal containers with a 20 gauge thick wall. It must be covered with a ball lid or with a lever closing system. These containers must be managed carefully by specialty businesses that store them safely. This avoids hydrozoic acid that contains water and even may burn skin if it has contacted with it. Adding to this, the container's outermost layer must be covered with a solid plastic box for avoid static building up inside the container. This process is necessary for controlling any explosion or breach in the bag. These companies help relieve danger from automobile recycling plants because when the car is completely flattened, it is impossible even to know if it has an airbag inside the car at the moment it was crushed. The problem with this is that because of sodium acid doesn't have any smell, it is not easy to perceive the presence of it. As many workers don't know the dangers of its components, they don't take the prevention necessary to avoid getting harm from airbag components. So as we can see, airbags save lives every day, thanks to our knowledge in chemistry. Chemistry is used in a process of functional airbag. There are three reactions that create the gas that take the impact for us, and it's also created in no time thanks to our own knowledge. But just as it can save our lives, it can also take it away. That's why we need to take care when we handle these substances, and always use the protections that are recommended, like for example using goggles or a protective suit so the chemicals doesn't have contact with your skin. When this is implemented in an airbag, there is a procedure that needs to be followed so the chemicals are not released to the air and cause damage to the person. Something we can do to manage the airbags after it had exploded, after it has saved someone's life, is to store it in a metal container with a solid plastic bag around it.
In my opinion, it is very important that we are aware and that we understand the processes that take place in our daily lives, such as this one. The functioning of airbags can be vital in life-threatening situations, so it is important that we know how this works, and it is important that we know the real-world application of the things that we've learned in class, such as stoichiometry and the ideal gas law and enthalpy, entropy, the Gibbs free energy, because in the future it is possible that many of us are going to work in related areas, and it is important that we know to make the right calculations and so that no lives can be at risk and so that everything goes out as planned. And yeah, that's what I think is really important about this activity, and I found it really interesting to actually see the real world application of what we've seen in class so far.
Understanding the uses of chemical reactions is very important in our daily life, because with that we can create products that can save other people's lives, like with the example of airbags. If we don't know how to handle some chemicals, we could get harmed, so it is also very important to notice the way that these chemicals react in order for not making any kind of chemicals explode. If they explode, they can harm somebody's life. So having knowledge of this, we can help other people by spreading the word and preventing them to harm themselves with these kind of chemicals.